Hello Professor, my name is Mohammad Usman from the Computer System Lab, and today I shall be giving you the presentation on a paper which is titled as SMS, a framework for service discovery by incorporating social media information. To begin with, I would like to give an introduction of this paper. It says that the adaptation of service-oriented architecture in the forms of web services, cloud services, APIs, and mashups are becoming very popular. So the discovery of services is becoming a key component, and these days it is facing some challenges, which includes a single source of description documents, which actually limits the performance of services due to the insufficient semantic information. So the authors uh, believes that more factors must be considered, since consumers place more demands on non-functional aspects including popularity, decay factor, activity, and personalization, etc., compared to the functional aspects. So existing discovery of services are based on semantic similarity, collaborative filtering, quality of service, and the social network. So the service providers tend to run on promotion on social media. So this paper tends to acquire social media information related to the APIs from the very famous social media website called Twitter. I would like to discuss a few issues that authors have basically addressed in this paper. These are how to reasonably model each social factor for services and how to design an effective combination strategy for social factors to generate service retrieval results with high accuracy. And the main contributions of the authors of this paper is a social media based service discovery framework which is named as SMS that has been proposed which utilizes 4 social factors, and these social factors are modeled from Twitter for the improvement of service retrieval. They also design a weight learning algorithm for the combination of these 4 social factors, and they perform comprehensive experiments which are actually conducted on the real world dataset that has been crawled from Twitter to demonstrate the effectiveness of the proposed framework. The authors tend to work on the Twitter list. The Twitter list was proposed to help the users organize the Twitter accounts which they follow, and it has been widely used to group the sets of users into a topical categories. Generally, list is created with a name and a description, and the creator can manage these list members. So for a Twitter account, the names and description of the list including it can be considered as semantic labels. In the figure, you can see that some social features of a famous website called LinkedIn, which has a account on the Twitter, is shown, and some factors can be seen, which is of tweet numbers, number of followers, the number of following which this particular Twitter handle is following, and the favorites thing. And for instance, the followers of the LinkedIn and the users interested in it, and the number of followers indicates the popularity of LinkedIn in this social network. We're talking about Twitter at this time. So let's discuss about the data analysis that has been performed by the authors of this paper. And in this work, they crawl 3,877 APIs official Twitter accounts with lists including them. The figure that you're seeing at this moment, it shows the distribution of number of APIs based on the number of lists including them. So one API can be involved in multiple lists, and the most reaches 84,511. So about 30% of the total APIs are organized by more than 100 lists, and 70% are included by at least 10 lists. So this kind of information reveals that the API information is full of richness. This figure illustrates the distribution of number of authors based on the number of lists created by them. So the total number of authors who created lists for 3,877 API is 658,878, of which only 3.8% created more than 10 lists. So it is kind of obvious that the most authors design lists less than 10, and the sources of the list are in wide range. In this figure, the author has tried to portray the correlation between the number of lists by which an API is included and the number of followers that an API has. And it also shows a strong correlation between the number of followers and the number of lists. This is the last figure in which they show the correlation between the number of lists an API is included in and the number of tweets that an API posts. So looking at this picture or this data distribution, it can be shown that there is a weak correlation between the number of lists and the tweet numbers, which means that a popular API might not have dynamic information, indicating that API might not be practical or even has been outdated. So now I shall like to discuss with you the which the authors of this paper has adopted, and they formally formulate the problem of social media with the help of two definitions. One is the query service matching modeling, and in this definition, they assume that customers or the consumers prefer services that are more popular and more active, since popularity and activity indicate the practical applicability of the availability of the service. And they also use the definition of modeled service. And in this modeled service, they use 4 social factors of service extracted from the Twitter. One is the list content, second is the follower number, third is the tweet number, and fourth is the list number. And these features in general reflect the social level characteristics of services, including the semantic similarity, popularity, activity, and decay factor, which are all non-functional. Now I would like to show you the architecture of SMS. Here you can see the authors have tried to divide this architecture into 4 parts. In the first part, they propose as the measuring of the first social factor, which is service semantics, which is mined from the Twitter list. And this part consists of data pre-processing, semantic similarity calculation by utilizing LSI model, which will be discussed later in the slides, on the list metadata. The second part is the building functions to measure 3 non-functional social factors, which I recently discussed, which are popularity, activity, and the decay factor. So all these factors are modeled in the first 2 parts. They are proposed, and then they proposed a weight learning algorithm in the third part. And the purpose of this weight learning algorithm is to find an optimal combination strategy for social media information. And in the last part, for any coming query, the new values of these 4 social factors that have been modeled, it can be generated and can be integrated based on the learn optimal weight assignment to generate a list of ranked results. Here I would like to discuss with you the leveraged Twitter list. As said earlier, that lists were introduced for users to manage their followings and the tweets they post. So the users can group a set of accounts whom they think have similar topics, and the list, it has also a semantic and the syntax that it is limited to 25 characters, and the list description that approximately shows the content of the list. Here in this table you can see the example of list that contains APIs which are selected from the dataset that are used by the authors. And here, for example, you can see the names of Flickr, which is a popular photography website, LinkedIn, which is of professional resource recruiter website, and Last.fm, which has the which is used for which is a popular website for music and DJ producers, etc. In the next phase, as we saw the SMS framework or architecture framework, the first part was the data preprocessing. And for the purpose of preprocessing, they use five different characteristics. One is the tokenization. So the purpose of tokenization is to identify the words that are being merged by the users. So which are often the users tend to combine two separate words, and they can post on their social media websites, and the purpose of tokenization is to separate these two words that are combined together. Next is the removal of stop words. So the stop words that are useless within the dataset, that includes a, the, about, etc., they should be removed. And in addition to these common stop words, a set of domain-specific words should also be filtered out, which includes Google, list, Twitter, or any other domain-specific word. And next is the identification of most important attributes, which are nouns and adjectives. So it has been analyzed by several previous works that nouns and adjectives in list names and descriptions are particularly very useful for semantic extraction. That is why the authors have proposed to identify the nouns and adjectives with the help of a tagger tool. Next is stemming. Uh, the extracting the stem words is also very important because they kind of add redundancy to the similar to the data set. So the words including travel, traveling, traveler, they are all stemmed into a particular keyword called travel, and so on for other keywords. And also the last part is the filtration of low frequency words. So as the definition of list names and descriptors is arbitrary, we know that some words with low frequency are regarded as impurity in the presentation of APIs, hence they are filtered out. Next is the latent semantic indexing, which is retrieved by the authors say that the information is generally retrieved by matching words in the documents. So the latent semantic indexing is a model which actually maps queries and documents into a space with latent semantic dimensions. So conceptually, the words in the document can be similar and then can be obtained even if they don't share any words. So a large collection of text is usually represented as a term document matrix X. The matrix X is adopted by the authors, and it could be in some other words too. So for it should be, it is noteworthy that the order of this term in the document is unconsidered in the matrix X on the basis of bag of words. So finally, instead of dealing with the raw term frequencies, the entries in the term document matrix X are often transformed, and an appropriate weighted technique, which is of TF-IDF. It is a widely used as a weighted factor in the text mining and other fields. So the TF-IDF value of each word increases with its frequency in the corresponding document. So for consider a word which has a high TF-IDF value, means that the frequency of this word has is more than the other words in the document. Now I would like to discuss with you the modeling of non-functional social factors, as has been discussed in the introduction section, that the authors have utilized the non-functional social factors into the SMS framework. So these non-functional social factors are incorporated. Uh, they use three factors. One is the popularity factor. So it is assumed that when a consumer is faced two similar functions, they are more likely to select the popular one. So based on this information, the authors have considered the number of service followers could reflect the degree of being concerned for the service. So more the number of activity, more the number of followers, the more popular an API is, and that is why it could be considered as a better option for a consumer to be selected for the service. Next is the activity factor. So service accounts could post tweets since they are users in Twitter. So generally the tweets could be or the retweets could be posted of about services or the trends. So that is why the authors have considered a service is active if it's post if it posts frequently on the Twitter, and if it is not posting very frequently, its activity factor will go down. Lastly, and the non-functional factor is of decay factor, and the service included by a list with very high frequency are likely to be too general for the consumers. So the authors have tried to damp the contribution of the candidate service that include by too many lists. Finally, all these side information in the are based on the form of triplets. They are defined and they are used by a weight learning algorithm that learns the query service matching function for all the triplets in the form of which they term as capital Z. Now we'll look at the an algorithm which is of weight learning algorithm for the social factors, which actually performs this collection of training triplets for the non-functional social factors. Here you can see the snippet of the algorithm, which in which the input consists of a collection of training triplets capital Z, which has a regularization parameter lambda, and the number of iterations denoted by capital T, and the learning rate beta. Initially, each social factor is assigned the same weight, and then the model is trained, and during each training iteration, the learning rate is set. So then a triplet is obtained from the collection of capital Z, and then respectively they compute the output for with the objective, which includes the objective function of the triplets. Let's have a look on the evaluation methodology. Uh, they use for evaluation a method of binary judgment should be applied to identify whether the returned API is relevant to the given query or not. So the queries used for evaluation could be chosen from the given dataset of 52 sample queries that are extracted from the topics of 12 categories as shown in this table, which is of music, travel, financial, e-commerce, mapping, sports, and etc. So the idea of binary judgment in the evaluation is that return result for a given query can be judged as relevant once its category is identical with the category of the query. So that is why they have used a binary judgment kind of protocol or algorithm, which will result in either 0 or 1. It will return a 1 value if the category of the query is same as the category which was demanded, and 0 in other sense. So this is the experimental setup. For the purpose of evaluation of this proposed weight learning algorithm, they have created a collection of triplets for training, and first randomly the part of predefined 52 queries are selected, which are used as training queries, and then they used this method for this this approach for comparison with different methods. The first method is PW, which is programmable web, so which is used for semantic matching by LSI model. And for in this paper, authors have set this method as a baseline. Next is the list only, which is used to which is used to compute the semantic similarity between using the LSI model for ranking APIs. And then is the popularity factor, which includes the number of followers. And then is the activity factor, which reflects the number of tweets. Then is the decay factor, which shows the decay factor generated from the API's list number. And then they have used a method of uniform, in which all the non-functional social factors are uniformly combined with the same weight. And finally, the SMS method is used for comparison. Here are the comparison and evaluation results. In the first two evaluation parts, randomly 70% of the 52 queries are used for training queries, and the collection of training triplets is generated. And the remaining 15 queries are used for testing purposes. So here you can see the effectiveness of Twitter lists. When compared with between the programmable web and the list only, the difference can be seen that in this table, it is observed that most of the queries, the list only outperforms PW, the programmable web, on the precision at 10. And in terms of normalized discounted cumulative gain, NDCG, at 10 cutoff value, the PW performs unstably. However, it tends to outperform list only on more than half of the occasions. Here you can see the results of method comparison. First of all, in terms of precision at K and normalized discounted cumulative gain at K, SMS, the proposed algorithm, always achieves the best performance among the all evaluated methods. So specifically, the authors have tried to find out the compared with the uniform method, SMS improves precision at K and NDCG at K by at least 11 and 3% respectively, which shows the effectiveness of the weight learning algorithm. So, and also the authors tend to analyze that SMS shows its superiority when compared with methods integrated with one non-functional social factor, which is of popularity, activity, decay, and which caused by the contributions made by the multiple social factors. The other thing can be seen from this graphs that when compared with the baseline, all other methods achieve better performances based on all three metrics, which shows the superiority of the incorporation of the social information collected from the Twitter. Finally, the uniform performs not so well as these methods are integrated with one social factors. So the authors have discussed that the reason for this performance of the uniform could be the inappropriate weight assignment for the list. So this brings us to the conclusion of the paper. I'd like to conclude that with the explosive growth of services, including web service, cloud service, APIs, and mashup, the service discovery is becoming a very imperative issue. And the authors discuss that it is feasible to incorporate social media information to facilitate the quality of service discovery, since the presence of services in the social network is rapidly increasing. So, in this paper, they have proposed a novel framework for service discovery, which is called SMS, which can to exploit the social media information collected from the Twitter. They also used functional factors with the help of LSI model and applied to mine the semantic information of service from the metadata of the list that contains them. So they tend to use a weight learning algorithm to retrieve the services from for a coming query, and in the experiment part, the evaluation results are presented, which are actually performed on the real world dataset, which are actually crawled from the Twitter. And finally, the results demonstrate that the effectiveness of social factors and the proposed learning algorithm is quite effective, and hence the use of a non-functional social factor actually enhances the social discovery service in a positive way. Thank you, Professor.